This is an experiment in giving you another example of accelerated motion, constant acceleration, constant velocity, mixing those together, that we don't have time for in class. I apologize for the fact that the video quality is probably not fantastic. I hope it's at least good enough that you can make out most of the writing on the board, and my babbling and pointing and things will hopefully fill in some of the gaps that you're missing otherwise. So that's what's going on here. I'm going to tell the story, and we're going to see it's a little bit different, like every problem is, a little bit different than the other problems we've done, but we'll see that we can solve this problem using the same methods we've used for all the other problems we've done, and come up with answering a question that, at least for some animals, is of very great practical importance. So here's the story. Out on the savannah, we have a cheetah that is going to chase a gazelle. In particular, the cheetah bursts out of the grass with a constant velocity of 27 meters per second square, or meters per second, 27 meters per second, and the cheetah can run with that velocity without slowing down at all for 15 seconds. At that moment, after 15 seconds, the cheetah becomes exhausted, because cheetahs don't have a whole lot of stamina. They can run very quickly, but they poop out pretty quick, and that I'll call the escape time. If the gazelle can survive until 15 seconds have passed, if it can get away and stay away from the cheetah that long, it'll be safe. So that's T escape is 15 seconds. Meanwhile, the gazelle starts out 140 meters away from the cheetah. The gazelle starts out far away, but it starts from rest, where the cheetah started in motion. The gazelle starts from rest and accelerates with an acceleration of 7.0 meters per second squared for a period of 3 seconds. After 3 seconds, which I'll call T maximum, T max, TM, the gazelle will have reached its maximum velocity, Vx gazelle maximum, Vx G comma M is what I've written down here. So after 3 seconds, the gazelle then is at constant velocity, its maximum velocity. So okay, that's our story. And you can see I've labeled the important, interesting events in the story up here. I've labeled the initial time and the cheetah's initial position, which, for the record, I'm going to choose to be x equals 0, with positive x pointing toward the gazelle. I've labeled the gazelle's initial position, and that's the same time Ti, T initial. It's two different objects, so they've got two different positions at the same time. I've then labeled the event where the gazelle reaches its maximum speed. I don't particularly care what the cheetah is doing at that point, but what I do care about is the Tm at time T maximum, the gazelle is at some particular position, x gazelle maximum, when it reaches its maximum speed. After that, the two animals will keep running at their constant speeds, constant velocities, until the cheetah tires out. So the cheetah is going to run until 15 seconds T escape have passed total. The gazelle is going to keep running until that same time. Now, if the gazelle is running fast enough, it will have kept ahead, and the gazelle will be farther ahead than the cheetah is at that time T escape, which means, hey, the gazelle has lived through this situation. If I go through the calculation and instead I find that the cheetah is ahead and the gazelle is behind at time escape, that's a sign that the cheetah at some point in there caught up with the gazelle. And let me tell you, in real life, the cheetah is not going to keep running. The cheetah is going to devour the gazelle. So that's our story. That's what we need to figure out is, does the cheetah ever catch up? Or more specifically, after 15 seconds, who's ahead? Is the gazelle still ahead, or has the cheetah had a chance to catch up? So I'm going to start by collecting data and writing down data for each one of these times. Each time has a couple events with it, and we'll write that down, and then we'll draw some graphs, and finally we'll sit down to solve the problem. So to begin with, my initial time, when the story begins, as usual, I'll call that 0 seconds. And as I said earlier, x cheetah at the initial time, I'll call 0 meters. That's just choosing my starting point for time and position. X gazelle at the initial time is 140 meters. So these are two separate events. The initial time in cheetah is one event, it's over here. Initial time in gazelle is another event over here, but it is the same time for each. Meanwhile, Vx for the gazelle initially is 0 meters per second. 0 meters per second, it's all good. So I could write down Vx cheetah, but that's going to be a constant, and so I don't need to write it down separately at each event. Only the velocities that might be changing do I ever bother writing down separately at each event. So I've got this. I've got this information written down. My next event is at the time when the cheetah, or when the gazelle rather, reaches its maximum speed. And so I called that T maximum of 3 seconds. I don't care what the cheetah's position is then, but the gazelle I do care. X gazelle at that maximum speed point. I care, but I don't know how far it's gotten there. I don't have any idea. I also don't know what Vx gazelle maximum is. I really wish I knew what the gazelle's maximum speed was. The gazelle wishes it knew what its maximum speed was, but we don't know that yet. So I also don't know the cheetah's position at that time, but it turns out that's not going to be an interesting question anyway. So that's also an unknown, but I'm not going to bother worrying about it for now. Finally, at the escape time of 15 seconds, I need to calculate the position of the cheetah at the escape time, which I don't know. I need to calculate the position of the gazelle at that escape time, which I also don't know. And I suppose I might wonder, what is the velocity of the gazelle at that escape time? I don't know, but it's equal to its maximum velocity. It hasn't changed. It's the same value. Okay, so that's my story. That's my story translated into knowns and unknowns. And my story there. Let's translate this into graphs, just so we can see what the graphs will look like. The velocity graph is pretty simple. The cheetah's velocity is a constant. I know exactly what it is, but this is just a qualitative graph to get a feel of how this is going to go. It's constant, except at 15 seconds, the cheetah collapses and falls down exhausted. So it's supposed to be a horizontal constant. It should look mostly constant. The cheetah's graph is that constant velocity that then drops down to nothing. The gazelle's graph is going to be a little different. The gazelle starts at 0 velocity, has a constant acceleration, but it's going to top out like this. So the gazelle's graph is going to be a constant acceleration section and then constant velocity on well past 15 seconds, since the gazelle has more stamina than the cheetah does. So that's our velocity graph. That's what velocities look like. Translating that into position is relatively straightforward. A constant velocity in velocity graph will translate into a straight line in position. So our cheetah will look something like this until 15 seconds, at which point the cheetah's position is constant. The cheetah doesn't move anymore after 15 seconds. On the other hand, the gazelle starts out ahead, here say. The gazelle starts out ahead, but we don't know exactly how much it's going to speed up. We know its speed is never going to be as fast as the cheetah's is. That would be one heck of a gazelle. Cheetahs are amazingly fast for the time they can run. But we don't know how fast it's going to work. It's going to be curving up from, we know the slope is 0 to begin with. It's going to curve upward, but we don't know how much. It might be a slow, gentle curve for 3 seconds that then leads off here and leads to a grisly death a little ways ahead, where the cheetahs, or where the gazelle's graph doesn't ever pass by the cheetahs. Or it might be that the gazelle speeds up just enough so that when I extend this forward, that might not have been just enough. That's where the cheetah would just barely get it. If I had something that sped up a little bit more, this one, the gazelle, this one maybe was caught right at the last possible second, but if it speeds up just enough before it levels off to a constant velocity, to a constant slope, maybe the gazelle will actually miss and dodge the cheetah entirely. That's what we want to find out. We want to just compare, if the cheetah just skipped eating the gazelle, I want to compare who got farther at this 15-second time. If the cheetah got farther, then that means somewhere before that it must have eaten the gazelle. If the gazelle got farther, that means the cheetah will never catch up. That's what we're looking for. That's what we're trying to solve for in this problem. Okay. So I've done my prepare step. My next step, I guess, is to go ahead and start solving the problem. And I'm going to go ahead and erase all this stuff, erase my setup. I'll leave the graphs there for now. And at this point, we can write down the constant acceleration equations for the gazelle. I'm going to want to fill in both of these unknowns about the gazelle. I'm going to want to know how far it's gotten and what its maximum speed is at the end of that acceleration section. I'll say, actually, at this point, to be completely honest, I don't know exactly what my strategy is going to be to solve this problem. All I know is that there are these unknowns in the middle that have a lot to do with how far the gazelle is getting and how fast it's going that I'm pretty sure I'm going to need. When in doubt, just start solving for as many unknowns in a problem as you can. So here, and starting with the earlier ones, not a bad plan, I guess. You might need them for later ones. So let's write these down. I have the constant acceleration equations for the gazelle. And so constant acceleration for the gazelle. And my initial point, my initial event is going to be t initial. And my final event, I go t initial going to t maximum speed. That's going to be my initial and final pair. So let's write down what those equations will look like for the gazelle between those two events. Well, I've got x gazelle max, or at its maximum speed point, equals x gazelle initial plus vx gazelle initial times t max minus t initial plus 1/2 ax gazelle times, running into my graph here, sorry graph, t max minus t initial squared. That's my first constant acceleration equation for the gazelle's accelerating phase. The second equation, Vx gazelle maximum speed is equal to Vx gazelle initial plus the acceleration of the gazelle times t max minus t initial. And finally, I've got that third equation, Vx gazelle maximum squared equals Vx gazelle initial squared plus 2 times the ax for the gazelle times x at the maximum point minus x gazelle initial. This is supposed to be x gazelle maximum, right? X gazelle maximum minus x gazelle initial. Okay, so those are my constant acceleration equations. And I can go through, I want to plug in anything that's 0. So what do I have? The gazelle's initial velocity is 0, and the initial time is 0. So gazelle's initial velocity is 0 here and here, initial time 0 here, here, and here. And I may as well note down what my unknowns are. I know all my initial things, so what my unknowns are seem to be the gazelle's maximum velocity and the velocity in the gazelle's position when it reaches that maximum velocity. So xgm and vxgm are unknowns. Okay, I think that's it. Okay, yes. So those are my equations. Let me simplify them down a bit just so that it's, oh, there was another thing that was 0. Vx gazelle initial is 0. Got to make sure that's there. Okay. So let's simplify these equations down and look at them. We can choose which ones we need to solve for our unknowns. We can figure out what we need. So I'm just going to copy these equations down up above here with the zeros plugged in. What do we have? Well, this one here gives me that x gazelle maximum equals x gazelle initial. This is just 0 times stuff, so that all goes away. Plus 1/2 ax for the gazelle times tm squared, t for the maximum speed squared. That one's there. Vx gazelle maximum equals 0 plus ax for the gazelle times the maximum speed time, the time it takes to get to its maximum speed. And the last one, Vx gazelle maximum squared equals 0 squared plus 2 times ax for the gazelle times this difference, x gazelle maximum minus x gazelle initial. Okay, I put that all together, underline my unknowns. Looking at this, my two unknowns are up here. I've got two equations that will just hand me, each one will hand me an unknown on a silver platter. So I'm going to keep those two equations as equations I'm going to keep indefinitely for this problem. I'm going to use those two. This third one, I don't need it so much because it's redundant once I have the other two, and the other two are already solved for the things I want. So okay, I've started that. That's great. Wonderful. My next question is, let's figure out how far the gazelle gets then by the end of the story, by the escape time. This is just, so that was constant acceleration for the gazelle. Next up, we're going to look at constant, no, I could plug in numbers to these right now. I could just plug in numbers and I'd have numbers for them. You could do that if you want to. If you do, keep units, keep track of units, keep all the sig figs. You need some extra digits for rounding error. But for now, we're just going to leave it this way. We're going to just leave it symbolic because I like symbolic answers. Next up, we're going to do the constant velocity once the gazelle is at its maximum velocity. So for the constant velocity part of the gazelle's motion, that's from the maximum speed time up to the escape time. Remember, we're assuming that the cheetah either doesn't catch the gazelle or decides to just run past the gazelle for unknown reasons to be able to solve the problem. So we want to know how far would the gazelle get by the time the cheetah gets tired. That means we're going to choose our events to be from the maximum speed time initial is our t initial, and we're going up to the escape speed time. The escape time is our t final. So that's our initial and final. And constant velocity, there's only one equation that we ever use for constant velocity, and that is the final position. So x gazelle at the escape time is equal to the initial position, x gazelle when it reached its maximum speed. That's the initial of this portion of the motion right here. Initial plus velocity, the gazelle's at its maximum speed, vx gazelle maximum, times t escape minus t at maximum speed, te minus tm. So that's what I've got. I've got my one constant acceleration equation here. Looking at that, nothing in that is zero, in fact. What unknowns do I have? Well, I don't know a number right now for the position of the gazelle when it escapes at the escape time. XGM is technically an unknown, but I have an equation for it. And the maximum velocity, VXGM, is an unknown, but I have an equation for that too. T escape and T maximum are known, 15 and 3 seconds. So those are knowns. So okay, I've got this equation. And this is going to be another equation that I will keep. So now I have 1, 2, 3 equations that I'm going to use. And hey, 1, 2, 3 unknowns, 3 independent unknowns in these equations. So that means I have enough information to solve for my final position of the gazelle. We'll plug in numbers in a minute, but for now, I want to come back and figure out what's up with the cheetah. And again, remember, the cheetah is going to be constant velocity again. The cheetah moves at constant velocity the whole time from its initial moment out until it collapses of exhaustion after 15 seconds. So that's what we want to set up for the cheetah. For the cheetah, let's see, so constant Vx cheetah, and for here, we don't care where the cheetah was when the gazelle reached maximum speed or anything. We can do this all in one whole calculation, going from my initial event time initial as my initial time to all the way to the escape time as my final time. That'll be what we do for the cheetah, initial to escape. That's the whole story. So let's see what we've got. Constant velocity, there's just one equation to worry about. In particular, we say here that x cheetah at the escape time is equal to x cheetah initially plus Vx for the cheetah times t escape minus t initial. And to simplify this, we plug in zeros t initial was 0, and x cheetah initial was 0, because that's where we chose our 0 point to be. So simplifying this equation, this just comes out to be x cheetah escape equals, actually, you know what I'm going to do? Well, I'll write it down here, then I'll simplify over there. X cheetah escape equals Vx cheetah times t escape. And what are my unknowns here? These were both given in the problem. Only the cheetah's final position is an unknown. Okay, so this is one more equation and one more unknown. I have 4 equations and 4 unknowns. I'm done with the physics. All I have to do is do a final comparison to get my story. So let me assemble my equations over there, just so I have room to do some algebra while referring back to these. Well, actually, you know what? I've got this here. Why don't I separate this out? I've got my equation for the cheetah. And really, at this point, I can plug in some numbers. This is equal to 27 meters per second times 15 seconds. Do I have a number for that written down? 27 meters per second. I should grab a calculator. Give me 1 second. In the future, when I'm making more of these, have the calculator handy. So what do I have? I have 27 times 15 gives me 405. So I get 405 meters is the distance that the cheetah travels in those 15 seconds. Clearly, it would have eaten the gazelle if the gazelle hadn't started moving really quickly. It would have eaten the gazelle. But we have to figure out where the gazelle ends up. I've got this equation for x gazelle, the escape time. Let me plug in my other 2 equations and see what comes out of that. X gazelle escape equals, well, this first one I've got an equation for. X gazelle initial plus 1/2 ax gazelle times t max squared. That's this first term that I've just plugged in this thing. Okay. My second term, I'm going to multiply Vx max times this difference in times. So my Vx max I have an equation for. So this is plus, plug in that equation, ax gazelle times tm is my Vx max times, and then let me write this down, I've got t escape minus t max. Now, this is another one of those cases where you would be perfectly welcome to just plug in numbers in this case. Now I just have one unknown in this equation. All the rest of these things were given. You're welcome to just plug in numbers. I am a compulsive algebra simplifier. I really like having my algebra simplified because sometimes I get interesting insights from that. So I'm going to combine some terms in here. This is equal to, well, the x initial is going to stay. X gazelle initial plus, now here's the fun part. I see that this is a 1/2 at squared. And over here I'm going to have a times t minus t, so it's going to be an at squared. Those are going to combine together. So actually, this is plus 1/2 minus 1. This is minus 1/2 ax gazelle maximum speed time squared. That gets rid of both of these terms. And then I'm left with plus ax gazelle times tm times te. Okay, that didn't actually give me any new insight whatsoever, but at least it's an equation. I can figure out how that works. So, I have an equation. Really, either of these is fine. I can plug in some numbers. Let's see what we get. X gazelle escape equals, my x gazelle initial is 140 meters. 140 meters. Then I'm going to subtract 1/2 times 7.0 meters per second squared times 3.0 seconds squared. And then plus, here I've got my 7.0 meters per second squared was my acceleration times t there, 3.0 seconds times t escape, 15 seconds. So I put those all together. I've got this whole big mess of stuff And, well, I can plug it into a calculator. 140 meters, let's see, this second term is 9 times 7 times 0.5 is, if I put numbers in here, the second term ends up being minus 31.5, and the units are meters per second squared times second squared is meters. So minus 31.5, I've got that. And then down here, I've got 7 times 3 times 15 is plus 315 meters. Added that in. And when I add that all together, I get X gazelle escape time equals 423.5 meters. That's what I just came up with putting this all together, 423.5. So where are we? Well, hey, the gazelle stayed ahead of the cheetah. It stayed ahead, so it never fell behind where the cheetah was going to be for the time the cheetah could run. The cheetah gets to 405 meters and collapses in exhaustion. The gazelle is still running 20 meters ahead. So there we go. The gazelle lives, and the cheetah starves to death and dies. So there's our story. We have the cheetah did not catch the gazelle, and I guess we should do sort of an assess step to see if these things make sense. I've already followed the units through carefully in each one of these, check the units to make sure they all come out right. We came up with a distance here, step by step. We came up with a distance here. It was just the right thing. Fast animals going half a kilometer in a quarter of a minute maybe seems plausible to me, seems not too bad. So that seems not, not outside the realm of possibility. And again, physics problems usually aren't written to be a complete blowout. There's got to be some suspense. The fact these numbers came out kind of similar makes me feel confident that the person who wrote the problem did a good job writing the problem, and maybe I'm in the right ballpark. So there we go. That's how we solved this problem. It was a combination of a constant velocity motion for the cheetah, start to finish, and a gazelle that had constant acceleration followed by constant velocity. And the two stories, we could have done the two calculations completely independently. We basically did. We did them independently, but they were linked by the fact that that the two stories had the same times at the beginning and the end. We were able to compare the two stories because we knew that there were simultaneous events for the two different stories. That the cheetah and gazelle initial event were at the same time, and the cheetah and gazelle final event were at the same time. And that was what let us tie the two stories together and answer the question. Just as an aside, there's another thing that you could have done if you'd really wanted to. We set this up to say, let's go until the escape time of 15 seconds and see if the cheetah has had time to catch up with and possibly pass the gazelle or not. The other way you could have set it up, if you'd really wanted to, was to say, I'm going to solve not until that escape time. I'm going to assume the cheetah can run forever, and I'm going to figure out just how long it would take for the cheetah to catch up. I could have done it that way. I could have come up here and assumed the cheetah kept going, and the gazelle kept going, and that there was an T food, where the cheetah is devouring the gazelle, and an X food where both were at the same position. We could have done it that way instead of this way, where neither of these would be known, but what we would know was that X gazelle at the food time was equal to X cheetah at the food time, because that's where the cheetah ate the gazelle. We could have done it that way. It would have been a slightly messier calculation to do it that way. I liked it better this way, but again, then the question would have been, when you solve for the time at which that happens, was the time less than 15 seconds, so the cheetah would have time to get there? Or if the time was greater than 15 seconds, that would mean the cheetah would poop out before it had time to catch up with the gazelle. That's another way you could think about it. And I encourage you to try it that way, actually. It ties the equations together a little bit more. It's a nice little example that way. If you ever do that, you'll find that it would take the cheetah 18 seconds. 18 seconds to catch up. If you tried that calculation, you'd find that the cheetah would catch the gazelle if the cheetah was able to keep running for 18 seconds instead of 15. It would have been a good catch there. So that either way would answer the problem the same way. We'd get the same gazelle lives answer. We have to. But it's your choice which way you set it up. There's no wrong way of doing it. You just need to be careful about what your way of setting up the problem is. So, with that in mind, this seems to be the end of our example, and hopefully you find it useful.